It always feels funny when you're introduced by someone reading words that you yourself wrote like a few hours ago, and then you sent in an email saying, I hope these aren't too late. But it's nice to meet you all. I'm Alexis. So I'm going to be talking about augmented reality beyond ARKit. Now, beyond sort of an aggressive word, right? ARKit's obviously amazing technology, as is the new versions of ARKit that we've learned about just yesterday. But despite that, there's still some things it can't do. You might have specific requirements that it can't meet because it's meant for something a little different. That's sort of our situation. I work at Topology Eyewear, and I'll get into that and what that means for our requirements. So this is probably a sort of familiar, horrifyingly green face. This face mesh is the one that ARKit gives you out of the box. So a little after the ARKit face tracking features were revealed, you saw a lot of apps that all had a very similar face mesh because this is the one that it gives you. This was released not in WWDC, but a little bit afterwards during a fall session. They had a special session just on face tracking with ARKit. And my talk, because our company is all about eyewear, is really going to be focused on ARKit on the face. So first thing to say is ARKit gives really good face. The face mesh you get out of ARKit is not bad at all. Even before you get to the face mesh, it gives you this information about blend shape locations. This isn't information about where objects are on the face, like where your nose is, where your eyes is. Instead, it's scalar values that can be used to understand facial expressions by representing details of muscles. So you'll have shape locations that represent, how squinted your right eye is, or if the bottom of your mouth is like tilting down a little bit. It seems like this must be this sort of API and underlying technology that drives something like animojis, where the phone looks at your face, makes some kind of inferences about what you're doing with the muscles that define facial expressions, and then can translate that into another face. That's not so relevant for what we do. We're more interested in the mesh. And the mesh you get from ARKit is pretty good. It's about 1,200, I think it is, vertices. And although it's not guaranteed to be so by API, all those vertexes are stable with respect to their indexes. So if you go poking around and find out which vertex index represents the right side of the right eye, that's always going to be that one. So although you're not given coordinate locations for here's an eye, here's a nose, you can sort of reverse engineer the mesh and say, okay, this is reliable. I'm going to use this to get information. So this was very exciting, I'm sure when lots of people realized they could make these cool apps with meshes. And it was exciting for us too, but like I said, everyone has specific requirements. In our office, first question that everyone was asking, where are the ears? ARKit doesn't give you ears. It gives you a mesh that covers the front of the face, but not ears. This is our mesh, which has a little bit more information. Critically for us, it has the ear. So those white dots there tell you, the top of the ear, the bottom of the ear. It's not really surprising, maybe, that your average face mesh doesn't include ears, right? Ears are not famous for being deeply expressive of personality. Like there's no saying that, the ears are the windows to the soul, right? They're not, I don't think, particularly useful for face recognition, for telling the difference between this person and that person. So a lot of the technology out there for doing face detection and face landmark detection neglects ears. But for us, it's very important. And to explain why, I should tell you a little bit about what we do and how we use AR, which is probably different from how many other companies do. So I'll say first how we use AR. Then I'm going to point out some things that ARKit does not give, which happen to be things we need. And then I'll talk about how we do AR without ARKit to meet our specific requirements. So how do we use AR at Topology Eyewear? So Topology Eyewear is a glasses company, not an AR company, not a machine learning company, not an AI company, not a computer vision company. It's just a glasses company. We make money by selling glasses. Not smart glasses, not glasses with lasers, not glasses with little screens that'll tell you words that you forgot, just glasses. But they're glasses that fit really, really well because they're all custom made to the exact shape of your face. That's the way they're different from other glasses. And this presents certain special requirements. For instance, since we don't have retail shops, and someone is about to buy a pair of glasses that they've never touched and can't see in person because it hasn't been made yet, people are going to ask themselves, what do these look like on me? So first way we use AR, as other apps have done, is just for shopping. There we go. In our app here, you can have a virtual try-on experience where you, after being entered into the system, you'll see glasses put on your face, and you can try different styles and see how they look on you. You can pan around and see how they look from different angles, so you can get a sense for how they look from the side. If you want to, you can zoom in and zoom out and see exactly what the material is going to look like. It lets you also build different color combinations. You can have two-tone patterns. We have different material used for the front of the glasses versus the temples of the glasses. So primary use for AR here is it's used to support shopping in a really critical way for what we do. But because, again, these are custom fitting glasses, we have this additional problem that you wouldn't have at other glasses stores, which is if you're buying it because we can promise you that it's going to fit really, really well, how do you know that it's actually going to fit really, really well? And this is one of the ways we use AR as well. The computer vision stack that's part of our AR solution builds this mesh of the face, and we don't just show you the mesh of the face sometimes as a way of impressing you, like, whoa, there's amazing science going on here. We're showing the mesh of the face as a way to prove, hopefully, and make clear to people the specific ways in which our product is going to be adapted to you. So in this view, which we call the check fit view, you can go through different parts of your face and sort of you'll learn, okay, this is the nose ridge, these are the ears, these are the eyes, and the computer vision work that we've done to identify these points is communicated to the user to sort of prove the value of the product, prove fit. And then the last thing, and I think we may be the only ones who do this, is these numbers that are part of our AR stack, which are part of measuring the face accurately. We don't only use them to tell a message to the customer, to explain to them what we're going to do, we actually use them at manufacturing time. So the numbers that come out of the computer vision are used to turn these slabs of plastic underneath, which is Italian acetate, which is what premium eyewear is made from, into the actual glasses. Now, how does that work? We use robots. I've been told that I shouldn't show the actual computer-controlled milling machine that we use because that's a trade secret. So I put this robot in instead. It's much more charismatic than our robot, so you can think of it that way. But we don't only use robots. We have a computer-controlled milling machine for the Italian acetate frames, and we have laser cutters for the metal frames. And the frames also then go through human craftsmen who will look at images of the face that we've extracted from the AR stack, look at images of product, make sure everything just works. And the end result of all this is glasses that are very specific. So, for instance, just to give I'm going to be done advertising glasses with this slide, I promise. But so just to give an example of what I'm talking about, if your nose is not completely straight, as mine is not, then for your glasses to fit perfectly, you need glasses that are not completely symmetric either. And that's what you see in the nose bridge here. The nose bridge, because everything's made from scratch, is like custom adapted to the mesh that was formed by the observations of the person. So, or there's other ways noses can be different. So this is how we use AR, and that gives a sense of what our requirements are. Now let me go into a little more detail here on what AR does not give and how you can see it doesn't meet those requirements. And then I'll talk about how we do what we do. So first thing it doesn't give is ears. That speaks for itself. But it's not just ears. Other facial landmarks around the eye region and nose are not conveyed in as much detail as we need for what we do. So that alone makes it probably unsuitable, even if we were to use Apple's ARKit mesh and add maybe our own ear detector on top. Second big point, easy one to explain, very banal, but the face tracking features in ARKit are not available on all the iPhones. They're only available on the iPhone 10, and that's not enough reach. We already get enough questions from people asking, where's your Android app? Surely you have an Android app. It would be very embarrassing if instead we were getting questions which were answered with, no, we don't have an Android app, and we don't have an iPhone 8 app or an iPhone 7 app. All we have is an iPhone 10 app. That would seem exclusive and not very smart. So that right away is a deal killer for ARKit as it ships right now on Apple's platforms. But the third thing, and the thing that is most important and probably relevant for other businesses as well, is accurate scale. Really accurate physical measures of scale. So on the store right now, there are lots of ruler apps, and I noticed in the keynote they were announcing a new measure app that could be used for measuring distances. I don't know if that can be applied to your face as well, but for us, we need accuracy is what drives quality, so we need an ARKit view that, as much as possible, can give physically scaled dimensions that are really as accurate as they can possibly be. So to give a sense for what we're aiming for here, the manufacturing processes that we use are accurate below the millimeter level. We don't expect to measure exactly below the millimeter level anytime soon, but that's what we're aiming for, and we need to get as close as we can to that range. So how do we do AR without ARKit? Because we need more landmarks than we have, because we need more iPhones than ARKit gives you, and because we need more accuracy than ARKit gives you. I'm going to go through the parts of the process by more or less going through the flow that a user would go through when they were using our app, and that gives you a sense of the different components and how we put them together. So one big difference from how ARKit works, one way in which what we have is less impressive, is that what we do is not real time. One of the great things about ARKit is you launch an app, it looks at you right away, and then immediately, second by second, it is able to track your face and do graphics that are augmented on top of your face through real-time face tracking. We'd love to have that, but we don't right now. What we do instead is we have the user take a short selfie video of themselves. It takes about 30 seconds. It's not a very painful process. You sort of hold your phone up like this, you turn right, you turn left, and we capture that video. And I'll say a little bit about how we're going to use it later. But the process of making the video capture relatively easy, making it something you can do in 20 seconds or 30 seconds with decent light, involves pulling together a lot of different pieces of iOS to make that easy. So this is what the flow looks like when you're capturing. But just to give a sense of all the ways we're using AV Foundation and other components here, first of all, we're using core motion for device orientation right away. That's so that we can make sure that the phone's up. If you just tell someone to take a selfie, they might do it like that, or they might do it like that. For our system to work, we want the videos that we get to be as uniform as possible. So we enforce that the device is held vertical by providing UI feedback if it's not quite vertical. And then that center in the area where you're meant to put your face is not just there as a guide. We're also using face detection, again, courtesy of AV Foundation, to make sure that your face is centered. This is, again, to make our videos easy to process, so we're going to be able to do our own AR simulations later on more easily. And we're not just detecting that your face is there, we're also giving you interactive prompts. Turn right, turn left. Funny, earlier versions of the app, we had some kind of complicated ideas about how to do this. There was a point where we even had a sort of sound and light show with like music and a moving visual indicator, and we'd like tell people to like move their head with the beat, and then the idea was they'd know when to turn their head when the beat changed. It was very impressive to look at, but there's a lot of UX challenges with asking someone to turn their head away from the camera while also seeing feedback that's coming back on the screen. And what we've ended up now with finally, after a lot of back and forth, is something much simpler, which is just that we're now using, again, AV Foundation to keep track of the direction your head is facing. So once we've seen that you've turned all the way to the right, then we give you an indication to turn all the way to the center, and then another indication to turn all the way to the left. So in addition to that, we're capturing video, but another refinement that we needed to make in order to capture video that would meet our purposes is we don't capture video with the default camera settings. So the default camera settings are chosen in order to hit a good trade-off of making sure an image is well exposed and sharp and looks kind of nice, doesn't look too grainy. But we're not really capturing these videos mainly for the user. That's part of it. We're also capturing these videos for our computer vision system. And our computer vision system really likes having sharp edges around everything. So the way we do this video capture is by making, again, using AV Foundation to do custom modifications to the way capture works, so we have higher ISO than we would normally do. That means the images come out grainy, a little grainier than they might normally, but we get really sharp edges, and that allows us to get this accuracy, this physical accuracy that's so important for everything else that we're doing. And then in addition, lately, AV Foundation will give you camera intrinsics, and we then use AV Foundation to encode metadata into the video itself, and we use AV Foundation to trim the video. So this is just giving a sense of that even if you're not using ARKit, even if you're putting together your own system, iOS still gives you lots and lots of technologies that you can use to piece together something that can produce similar effects. If we had a full real-time system, we wouldn't need this, but given that we don't, it's really great that we didn't have to write all this stuff ourselves. So the video goes up to the server, and that's where we do computer vision on it. This isn't a computer vision and machine learning talk, so I'm not going to go into all the details on this, but suffice it to say, it's a very significant piece of code that we've built up. We're using many open source libraries, then we're using our own code written on top of it that coordinates them. I was looking through it recently, and I think it's more than 80,000 lines of code. It's Python and C++. We're using convolutional neural networks, so take a shot if you're playing a drinking game in the back. We're using ensemble regression trees. We have dedicated feature detectors for different parts of the face, for the ears, because they're so precious to us. Broad picture, what's happening is we take the video. We then pull out frames from the video, so then the video is just a bunch of images to us. If you stretch out the images, we throw away some of them, and then we have a few that are enough to provide a good sort of scrolling experience when you scroll back and forth. On every one of those images separately, we have a model that runs and does face detection, and then we have models that run and do landmark detection to find important parts of the face. So now you have a bunch of 2D images that all have 2D locations for important parts of the face. Then you take all those 2D images and you use that to build a three-dimensional model using a process called structure from motion. This is conceptually the same thing that you'd do if you were moving a camera around a single object. That's why it's called structure from motion. The idea is like the camera's moving, like maybe it's in an airplane that's flying overhead, and you want to infer the three-dimensional model of the city. But in our case, instead of having a camera moving around your head, we just have you turning your head. In earlier versions, we actually did have people move the camera around, and then we realized it's easier to just have them turn their head. It produces the same effect. We've also, because the detectors and other components of this are machine learning models, it's worth mentioning that part of what goes into this is a very large training data set that we accumulated ourselves. And I'll talk a little bit later about how we did that. So this is the server-side component. When the worker servers have completed building up the model, then this is made available to the iOS app, and then we're back in iOS. And now comes not the computer vision part of our AR stack, but the visualization and graphics part of our AR stack. And again, here we're just leveraging iOS. It's not all done in a Unity view or something like that. To be exact, we're using plain old SEN scene view, SEN view, to render the glasses, and we're just compositing it directly on top of UI image views that represent the face. So what you can see here is a cutaway of the view stack in Reveal, which is, by the way, a great visual debugger. If anyone's looking for a visual debugger, I highly recommend Reveal. And you can see where it's turning, how there's a split between the image in the back and the glasses image that's put in front. That said, if you look at that, there's some details which are made possible by all the work that was happening in the stack. So we have 3D models of all our product, and the scene view can render that, but it's the work that was done on the back end that provides information about exactly where to position the glasses, exactly how they should be reoriented. It provides information about the actual 3D shape of the face, which is necessary for occlusion. The fact that the temples can't be seen through my face is because we have a model of the face, we know it's there, and so we can occlude parts of the object that aren't relevant. And the details of the head pose are also being picked up for every frame. So in a much earlier version, it really only gave a good effect if you held quite still and just turned your head, as our CEO got really fond of demonstrating when we had some improvements made. This new version, you can like move your head around while you turn, and the glasses will follow it. And that's all because of work that's done on the server side to provide the app with that information for every frame. And then the AR effect of being able to scroll around and see the view from different images, that's just a gesture recognizer picking up a scroll view, and then the scroll view's action is driving new image views underneath and new rendering of the scene view. There's one more subtlety to this that might be worth going into a little bit, which is that for the rendering, we're not just using SceneKit as a high-level scene graph library. We also have some custom metal shaders that are used. One way in which they happen to be used right now is that in our app, we provide the opportunity for the user to customize their glasses. So we guarantee everything's going to fit, but if for whatever reason you want to have glasses that are taller or a bit wider than our default styles, you can do that. You can actually go in with sliders and make adjustments. And those adjustments are actually being translated into code that's coming down and running on the shaders. So that's the sort of big picture on how we put together our AR stack and how we use it. And the question that you then have to ask, especially when you think about all the work we're doing on the server side, is, gosh, is that worth it? It's a lot of work. And it's all to put together something that in some ways is better than what Apple offers for our purposes, but in other ways is less slick. We're not doing real time right now. Here's a comparison I thought of as I was trying to describe it. ARKit, yes, works out of the box. TopoKit, we don't really call it that. I just wanted to give it a name. Well, it works on all the iPhones, and that's critical. And it gets ears, and that's critical. It's not good if you have glasses and they like fall off your face because you don't know the exact distance of the temple length. And it has the accuracy that's needed for eyewear. So it's worth it because it's absolutely necessary. But then you might ask, is it really absolutely necessary? As I was thinking about this and experimenting with ARKit, it led me to a puzzling truth about the true depth camera system, which I hadn't seen reported anywhere else before. Background for this, as you may remember, is that only the iPhone X offers you ARKit face tracking experiences. And that's sort of intuitive, right? Because we all know that the iPhone X has this special sensor assembly in the top. The sensor housing, as Apple calls it, or the notch, as we all lovingly know it. The key part of that being the dot projector that's there on the far right. Here's an even cooler image. So what the dot projector is doing is it's creating a depth sensor because it projects out little infrared dots, and then the camera looks and sees the dots. It can see how far they've spread from each other, and I think that's what it's using to infer how far away an object is. Because if you don't have something like that, and you just look at a 2D image, you can't infer scale. Like if I give you a photo of a face, you don't know if it's Mount Rushmore or if it's a G.I. Joe. You just know it has the proportions of a face, but you don't know physical scale. And physical scale is important for doing this stuff well. If you thank you, iFixit for this, but if you get an infrared camera, you can actually see the dots that are projected. So you might find yourself thinking, makes total sense that ARKit face tracking is exclusive to the iPhone X, right? Only the iPhone X has the true depth camera system, so only the iPhone X can provide AR face anchor, which is the component used for tracking, since the depth sensor is what enables it. But there's a bit of a puzzle there, right? Because if Face ID is so accurate, as I perfectly believe it is, that we can use it and trust it with our secrets and use it for security and authentication, then how come ARKit is not? How come the ARKit face tracking is not accurate in the same way as we've observed? And one thing I realized is that actually the depth sensor doesn't seem to be used at all by the ARKit face tracking system. You don't need an infrared camera to do this. All you need to do is write a little app like I did that presents the ARKit face mesh, cover up the depth sensor, and you can see that it keeps working fine. If you cover up the depth sensor, Face ID stops working, but ARKit face tracking does not. It works just as well as before. So ARKit doesn't use the depth sensor? No, ARKit doesn't use the depth sensor. Why? I don't know. As my mother says, you tell me and we both know. Is this still true for ARKit 2? I don't know. That's one of the things I'm going to check as soon as I get hold of the betas, because I noticed that in the keynote they mentioned more accurate face tracking as one of the enhancements. So maybe they built the Animoji system, I think was acquired through a third-party acquisition, and then they repurposed that technology for the face tracking, and they never actually integrated it with the depth sensor, would be my guess, but I don't know. But anyway, bottom line is, it's still worth it for us to do what we do because we fundamentally need accuracy for our business. Now, to give a sense of this, let me talk about like one more example. So, you know, who needs custom fit glasses, right? That sounds like a real sort of first world problem, like crazy luxurious thing. That, to be honest, that's what I thought when I first heard the idea years ago. But it turns out that there are a lot of people who have persistent problems shopping for glasses that fit them. If you don't have that problem, then you wouldn't guess it. But there are people who, whenever they go to glasses shops, they don't find glasses that fit, often because their face is smaller or bigger than the stock sizes, or because they have a lower nose bridge. A lot of glasses out there right now in the United States are designed with the assumption that you are a Caucasian and have a Caucasian nose, but that's obviously not the case for everybody in the country. And so the very fine adjustments that we're making for custom fit glasses are not for the sake of crazy luxury, although we believe our product is premium and we are proud of it. They're for the sake of creating glasses that are totally comfortable for somebody. So this is an example here showing, I think I want to pass through earlier, showing the difference in nose bridge for glasses that are designed to be comfortable for an individual who has a lower nose bridge and the nose bridge for an individual more like myself. And you can see how subtle these distinctions are. This is why the accuracy matters. But even putting aside the importance of accuracy for fit, even forgetting that entirely, you really need it for optics. So this is a good example to walk through that. Pupillary distance is the distance between your pupils. And when you go and get your prescription from an optician, they often won't give it to you. They'll just give you your prescription, but they're a bit coy about that because they don't want to maybe give you all the information that you need to go somewhere else and get your glasses done. So when people give us their prescriptions, we can't rely on it having pupillary distance. Also, a lot of opticians are a bit, they might not be super exact about measuring it. This is the instrument that's used for measuring pupillary distance. It's called a Pupil Lammeter. To use it correctly, you stare into one end of it, and then someone else is looking in the other end, and they match a line with the pupil of your eyes, and from that they make the measurements. From my description, you can see that the way Greg is using it there is completely inaccurate. That's my colleague, Greg Hugh. Hi, Greg. Because you can't see anything really when you just look through that. You need to have someone on the other end looking at your eyes to measure it. And this other image here is a mesh got from the ARKit system provided by Apple, where I built an app to measure pupillary distance just using ARKit. So you can see here it's telling you my pupillary distance is 65 millimeters. So I've been waffling on and on and on about accuracy, but what do I actually mean by that? Here's a small sample. I think we have a bit more data, but this is a small sample of error in ARKit measured in millimeters over different individuals when you try to measure pupillary distance by using what ARKit gives you. Notice that for Greg, it's 7 millimeters off. Persistently, you keep measuring him, it keeps being 7 millimeters off. I don't know why ARKit does that, but it does. The point is these errors are higher than is really acceptable for our purposes. If you look at it, the root mean square error from ARKit is on the order of around 3.5 millimeters, where the max error that we see is around 7. Our system gives us an error of around 1.5. But really what optics requirements, we need to be under 2. And I think opticians are usually getting around 1 to 2, depending on how carefully they handle a pupillometer. In addition to some subjects being consistently wrong, when you use ARKit for individuals who have facial hair, the measurement changes different times. So there's a lot of inter-trial variation in the scale measurement of a face. So that's sort of what's driving us here. You may have noticed some other places mentioning that they use ARKit to measure face to like fit, say, glasses on you perfectly. But there are reasons to think you can't do it as perfectly, as you'd like to, because this is what the numbers look like when we measure them. It's very hard to measure it accurately. So we, in fact, to do it, have a whole separate flow in the app, which is just around the process of getting a pupillary distance measurement. If you'll notice, what's tricky about this flow is that it uses the back camera. You can probably guess why, right? We use the back camera because the back camera has higher resolution. It's a better camera than the front camera. So if what you want is maximum accuracy, you need to ask someone to take a selfie with the back camera, which they don't do often because, again, you can't see the screen when the back camera is pointing at you. And if you go to some websites, they'll say they can measure your pupillary distance just by taking a single image with a webcam. In our experience, that doesn't actually produce an accurate result. So if you want really good optics, you're not going to get a good PD measurement that way. which is why we have to ask people to take a video of themselves with the back camera, which is awkward. So we have to do a lot of work to sort of streamline the UX of this. We use voice signals, we use vibration signals, we have this nice video to make it as clear as we possibly can. All of this is, again, just to reduce accuracy, and it's like what you want to do if you're building a computer vision AR system that is different from what you get out of the box. As I mentioned earlier, one of the things that makes this tricky to complete is you need a lot of data because you're building machine learning models. So I thought it'd be fun to say a little word also about kind of machine learning startup style. A lot of the big names in machine learning are big companies like, Google with their TensorFlow library and Facebook with PyTorch, and we know they have these huge data sets from observing people and people's behavior on the web. But really, anytime you take images, you can get a huge data set pretty quickly with a lot of images. But how do you manage a lot of data if you're a small company? How do you do that if you're a startup? So data collection is hard. This is our DSLR rig. So you probably can't make it out here, but what this shows is 8 different DSLR cameras arranged in an arc, and then that blue seat in the center is where someone will sit. And then the lighting gives you nice lighting, and you simultaneously take 8 photos. And because these are DSLRs, you're getting very accurate photos. So you can use those to build a very accurate 3D model. And this is the ground truth that we use for training the model. So every one of the samples that we start with for data began as someone sitting in this chair, having 8 photos taken, building a 3-dimensional model, and then having human beings go through and manually annotate all the important points on the face on that 3D model. You can imagine it's a laborious process. But even if you had magic fairies who could do the annotation for you, just getting a lot of people to sit in a chair and have 8 DSLR photos and then also do the iPhone selfie dance to get that video to use that for inference in the model, that's also hard. So how do we solve that problem? So we used to be based down in Bayview, San Francisco, which is a little different from where we are now. And there's this cafe called Craftsman and Wolves across the street from where our office used to be. And we'd go across there for lunch because it was like the only place you could go for lunch except for a taco truck. And we were sitting there like wondering about how we could get more data. And it's funny, if you listen to Accidental Tech podcasts, I'm sure you guys all listen to Accident. It's this podcast about iOS stuff, and they have this great anecdote where someone wrote in describing what they thought was the process of having contributed data to Apple's Face ID system. But they didn't know it was Apple because it was all done secretly, right? I think they got an invitation to be part of a thing. They went into a room. It was like a white room. They sit in a chair. There's this white object where you can't see what it is. You can only see the lens. And then they had to stand there and go and follow some instructions, and their face was taken. And it sounded like the scene in the movie where the alien spaceship lands and you're taken in and scanned in ways you don't understand. And that's how you can get data if you're Apple. But our system was different. We're well, this cafe is great. Everyone in the neighborhood comes here, different kinds of people. And we all come here and eat sandwiches. And that was our answer, sandwiches. It was staring us right in the face because it was across the street. So we just put flyers in the cafe saying, if you want to get a free lunch, just take this flyer and come to us across the street. And we'll scan your face. It'll take about half an hour, and then you'll have a free coupon for a lunch. So that was it. Our database was built on sandwiches. But a lot of sandwiches, right? So, if you think about it, that's a few sandwiches, that's a dozen, but we have hundreds, thousands of items in our database. You're talking about lots and lots of sandwiches. Lots of people sitting down, getting scanned, and you give them a sandwich. After getting them signed legal papers. So that it's okay to use their face. So what are the conclusions here? I think just to recap what I say here, ARKit is awesome. It's magical, and it makes things super easy. And if I go and download the betas and find out that everything that we do now can be done with ARKit 2, we'll be switching to ARKit 2 as fast as we possibly can. But ARKit was meant to solve certain requirements. And if those aren't your requirements, like they weren't our requirements, you can do it yourself. you should also think about what your requirements actually are. Like, it would be nice for us to have the real-time effects, but what matters more for us is accuracy, which is why it's okay for this slightly more awkward flow that requires someone to take video. And, you know, if you're a startup and you're just trying to put together something that'll work for what you do, keep it simple. Think sandwiches, not spaceships. That's what I have to say. I'd like to be allowed to take any questions if anyone's wondering about any of this.
So how long was that process for you to go from, okay, we can't use ARKit, what are we going to do? Let's build our own. Or actually, I guess you started before ARKit existed.
Yeah, we started before ARKit, but as soon as ARKit came out, we were looking at if we could replace what we built with ARKit, because it would just be easier to have Apple build and maintain the stuff. Mm-hmm. But the entire process of building out the computer vision stack is a years type process.
Hey, I was wondering how do you do the occlusion of the glasses? Because it seems like you're sort of mixing the 2D and 3D.
Yes. Well, I can talk about that in more detail, but it's done in the shaders for the glasses themselves. So I suspect actually that we're not doing it in the best possible way, because I was reviewing some of the code that we use for calculating occlusion on the glasses, and we're calculating multiple maps and then doing it manually. I'm not describing it very well, but I can talk to you later.
Hi, so I was wondering, do you have an Android app for this? Or, like, do you ever plan to get one?
No, we don't have an Android app yet, but we're not restricted to the iPhone 10, so we have that. But it's on the App Store right now if anyone wants to try it out. So we get this question. The reason Android would be harder is the kind of usual reason. Hardware fragmentation means that I think just development would be harder, full stop. In particular, the models we have been trained with knowledge of iPhone cameras, so it wouldn't just be the usual Android hardware fragmentation. It would also be understanding the variety of optics of all the different Android systems. Up in front.
Are you finding any binocular vision issues with clientele through the video? Eye tracking?
I don't understand the question, I'm sorry.
So some people will have an eye that will maybe drift to the right or to the left.
Oh.
And you might actually see that during the process of a video that's where a person may not actually know that they have that condition.
To be honest, I don't know. I know that we've dealt with a number of customers that have special requirements around how they want the glasses to be or around their vision problems. But our whole process for selling a pair of glasses is not automatic. Although we use computer-controlled milling machines to build them, it's very manual. There's a human attention, and there's a back and forth in communication with people. So when we get special requirements, we're just talking to people to understand them. Also, when people buy glasses, they get a prototype version built out of mock material just to make sure the fit's right. So to be honest, I don't remember if we've dealt with those in particular, but I know we have dealt with some kinds of special cases like that. It's just part of what we do.
I really appreciate how you're catering to different nose bridge shapes and stuff like that. I was curious in terms of the facial topography, how much skin color, if you had to work any issues around that, and then also likewise, bangs or with women, they tend to have long hair.
Yeah.
When you're trying stuff on, you may want to pull it up for the scan so you get the ear, but then your style may be to have it down over your face.
So hair is an issue. We can't see through hair, but when you do the selfie capture flow, you get some guidance in the beginning to pin your hair back, and we hope people do. You also get guidance to try to do it in a well-lit environment, but still lots of people do it just sitting on a sofa in a kind of dark room. So you can provide advice, but usually if someone's going to purchase, they'll take the time to do a nice picture so they can see how it looks. You know, if you do a selfie with your hair down, you can still probably get a preview, but what's happening then is that the model is making an educated guess about where your ears are because it has seen lots of faces. But if you want really good fitting around the ear, you should make your ears visible. You had a first question before that. Skin color topology. Yeah. Part of the advantage of the sandwich-based data collection system is you get all sorts of people. So our model has seen all sorts of skin colors. To be honest, I don't know if it performs it doesn't perform badly on any particular skin color. I'm not sure how much variation there is, but I think the key there is just having training data that represents your test data.
With darker skin, you have brighter highlights, for example, depending on your lighting situation, and that may accentuate what's going on with your face.
That makes sense.
Did you consider, for the problem of pupil distance, using the flashlight and the way it casts a different shade on your nose as you're turning?
No. I don't understand that, but that sounds very intriguing.
If the phone is a different distance, it will cast a different shadow as you're moving with your nose to your cheek. You're welcome.
It's okay. I'm going to write that one down.
How many vertices does your ARKit have?
I don't think I would want to say right now. But actually, because I don't remember, I'll talk to you afterwards.
Like on an order of, can you give me a order of magnitude type of thing, or?
I can afterwards.
I see.
To be honest, I think it's around the same order of magnitude. So it's not the number of vertices, it's about accuracy. And I'd say our mesh is specialized around fitting eyewear. I think it's the world's best model for fitting eyewear. So if you want a really accurate read on your chin, we don't really do that because until someone invents eyeglasses that rest on your chin, it's not important for us. So it's concentrated around nose bridge, eye, ear, those areas.
Hey, so it looks to me that apart from the iPhone 10 limitation, there is a real trade-off between real time versus accuracy. So even if ARKit would work on older devices, you would still have the accuracy problem, right?
I don't know. I suspect that if ARKit 2 uses information from the depth sensor, it could be much more accurate than the current version of ARKit. So I think if you use the depth sensor intelligently, you could probably get very accurate information. And yeah, I don't know if the real time imposes inadequate accuracy, but that's a good question. That's something I'd like to understand better.
Just popped into my head. Do you have medical staff on your board of directors, or are you working with other medical companies? Because I could just see how this could really explode into other areas of custom design.
We work with ophthalmologists, so we have knowledge of how people sell glasses normally and medical information about how you do that. But really, we're just focusing on eyeglasses right now because they're rigid objects, so that they're in a sense an easier case than other kinds of custom things that people put on their bodies. They need to be very good because you're always wearing them. Every time someone thinks of how you look in a photo, they're thinking of how you look with your glasses. So there's a number of reasons that make glasses a good first case for this kind of product, I think. All right, well, thank you very much.